Okay, hello, back. We're back to finish chapter 6 this time for sure. We're going to do the last two sections of the chapter, which are 6.7 and 6.8, exponential and logarithmic models and fitting exponential models to data. So let us get it started. I'm going to get rid of the picture here and go directly to problems. Okay, so before we start, I want to talk about a few concepts you might hear about and you should know, and that is something called order of magnitude. So let's say order of magnitudes refers to the power of 10. So that's what order of magnitude is. So if this is 1, that's 1 order of magnitude. If it's 2, that's 2 orders of magnitude, and so forth. Now, if something is, let's say, 8 times bigger than something else, let's say we say B is 8 times bigger than A. Now, to use order of magnitudes, we have to see 8 times bigger is closer to what power of 10? Well, 8 times bigger is like 10 to the first power bigger, right? So in this case, we can say B is 1 order of magnitude bigger than A. Okay? So suppose, let's say, B is, let's say, 95 times bigger than A. Well, 95 times bigger is closest to what? To 100 times bigger, which is 10 to the second power. So we say B is 2 orders of magnitude bigger than A, right? So that's the idea of orders of magnitude, okay? I wanted to mention that in case some of you hear it, that's what it means. All right. So now what we want to do, we want to do some of these application problems. So it's number 6 here, says, let's copy it and see what we have to do. So what we have to do here is, it says that the temperature of an object in degrees Fahrenheit after T minutes is given by this equation. So temperature after T minutes is given by 68 e to the power of negative 0.0174 T plus 72, right? That's the exponent of E, right? And that's 72 over here. All right, so 68 e to negative 0.0174 T. So that rate is negative. That means the temperature is going down, right? So the temperature of an object in degrees Fahrenheit after T minutes is represented by equation that to nearest degree, what is the temperature of the object after 1.5 hours? Now, first of all, T here is time in minutes, right? In minutes. So that means what? That means 1.5 hours has to be represented as what? As 1 hour is 60 minutes plus half an hour is 30 minutes, so that's 90 minutes, right? So what we want to know is what is T of 90? And we can do that using a calculator. So we can put the function in here in y1, right? So y1, you press y1 here, and then put the function there, 68, and e to the power second, you turn the second on and you go to e to the power, which is second e to the power is right here, right? Okay, e to power of what? Negative 0.0174x. Close the parentheses, that's the power of e, you close the parentheses, and then you put plus 72. Alright, so that's our function. Then you can get out of here, second, quit, go to home screen, and then go to variables here, and then y variables, and then function, and is the first one. So y1. Press enter, and then put parentheses 90. 90. There. So 86.2 degrees is the answer. 86 point, whatever that was. 86.2 something. Now, if you don't do any rounding, that's what the answer is going to be. Answer here is a little bit off. So the answer in the calculator is actually correct. Okay? Because we put the correct function in there, right? Let's see. 68 negative 0.0174x plus 7, that's correct, okay? So what we got in the calculator is correct. It should be 86.2, okay? So that's how we do this problem. Now, let's do another one. Now here it says for the following exercises, use the logistic growth model. Now, first of all, let's see, can get this whole thing. Well, no, let me make sure we can copy the whole thing so we can answer all the questions at the same time. A little bit more. All right, that's good. So let me grab this whole thing. I'm gonna grab it from here, and we got lots of room there. Alright, so what we want to do is, first of all, I want to talk about what logistic growth means. So you know exponential growth, for example, something like this, right? That is exponential growth. That means it grows, just goes to infinity with no limit, right? So if you let this go, it goes forever, right? It goes just with no limit. Of course, things in nature don't grow like this, right? So what happens in nature is that first the growth could be exponential like that, but then eventually it slows down and it flattens. For example, if you put a bunch of bacteria in a dish, right? Now at first they grow really quickly, like that. And then gradually there is no space or food available. Then they slow down, right? Right here, they slow down and then it flattens, right? So that right there is the capacity of something growing. So we say on this dish, for example, the number of bacteria has this capacity. It's going to grow fast and it's going to reach its capacity, then it flattens. It's not going to grow anymore. So this point right here is called the inflection point. Notice that the curve behaves differently. See, it's increasing, it's called concave up, and this one is called concave down. So it's increasing to a certain point and then it slows down. Now recently, the COVID-19 disease or coronavirus is increasing exponentially in every country. Every country it reaches, it starts growing increasingly exponentially like that. Now, if you let it go, it's going to go through the whole society, let's say Houston area, right? If we let it go, it's going to go exponentially and it's going to infect everyone, right? Eventually, it's going to infect basically everyone because nobody has immunity to it, right? So it's going to go exponentially. And eventually, it's going to slow down when the number of people to infect is smaller and smaller. It's going to slow down at some point, and then it's going to slow down and flatten. When does it flatten? When everyone is infected already, right? Now, it has a fatality rate of about 1%. So if 2-3 million people in Houston area get infected and 1% on average die, that's a lot of people. See, let's say 2 million. What's 1% of 2 million? 200,000 people. Do we want 200,000 people to, to die? 20,000, 1% of it is 20,000 people to die just in Houston area? 20,000 people die just in Houston area? No. And if you expand it to the United States, that would be a whole lot of people. Remember, 30 million people, right? 1% of that, that's lots of people, right? That's 3.3 million people. That's a lot of people. So we don't want it to actually run its course. We don't want to do that. Even though some governments, like in Britain, they wanted to do that. In fact, here in the US also, we are about 2 months late to control this thing. So now what happens if we control it? Well, it slows down, right? Slows down like that, and it reaches that capacity like that. Now that happens in much lower. Here I graphed it at the same height, but it's not at the same height. So the capacity of it, of course, people are going to get infected, but it's going to happen what? Much slower. And then there is a capacity of the hospitals. Let's say our capacity of hospitals is over here. That means number of people who get sick can be taken care of. So about 15% of people who get the disease, they are going to have to be hospitalized. 10% of them need hospitalization and they'll be okay. Certain part of these people are going to die. And then about 5% of people not only need hospitalization, they also need ventilators. So we have to make sure we have these, and a number of these people will die, but if we keep them in a hospital, if they're taken care of, much smaller number will die. So that means when you slow these down, slow the growth down, you don't reach the capacity of the hospitals, then you can take care of those who get sick, right? And if you take care of those who get sick, then we can save a whole lot more people, and so this number would not be that big. But right now that I'm talking about this, we are about 130, 150 something in Houston, number that died of this disease. So hopefully we're not going to open up and stop having social distancing. I know it's hard on many people, but the government's supposed to take care of basic needs until we can get out of these crises. But that's the idea of logistic growth. So, and I show you, this is the graph of the Hubei, China, and that's how the number of cases were increasing. And it was February 11th or so, right here, they started having social distancing, and they slowed it down, and by this date, about here was flattened, right? So that's the logistic growth based on actually the actual data from Hubei, China. All right, so so that's the idea of logistic growth. Now here in this problem we are given an equation for logistic growth, and the equation for logistic growth is just this right here. Now with the calculator you can do logistic growth. Let me show you. So if you have a bunch of points and you think that the equation for it is logistic, then the calculator can find that for you, right? So let me see, do I have anything in L? I have something in L1 and L2. So if we think is logistic, then we can graph it. So I have L1 and L2, I have some data in there. Obviously this is not logistic, but I'm going to show you how to find it. So we go to stat, we go to calculate right here, and then we can go all the way down to logistic. You see it? And then we do, before I do that, let me change some of these. Let me go to stat and change some of these numbers because they're all the same and that doesn't work. So here we go, let's do that. All right, so I'm just gonna, the data of course is not, so second L1, and then we put L2 in there, comma, not sure why, there we go, comma, and then L2, and of course it's not going to give you my data is not logistic. I just want to show you the equation. You see the equation? So let me put it here. So the equation looks like y or f of x equals to, there is some c, and then 1 plus what? A times e to negative bx, right? There. So that's the logistic growth, and that's what the calculator uses to find an equation for you. So if you think about this, when x goes to infinity, when x goes to positive infinity, this e to negative infinity goes to 0. So this part goes to 0. So what we have is c over 1, which is c. And this number on the top is called the capacity. So that c is actually this line over here that this function is approaching, right? So that's the formula for logistic growth. Looks like it's kind of exponential, but it's logarithmic. Logarithmic first, exponential, and then it's logarithmic. So it's like exponential and logarithmic kind of mixed together. All right, so here's an example. It says find and interpret f of 0. So this is a general formula, and in this problem we have, of course, this formula that is given. So let's write it down so you can see it. So in this problem we have f of x is 150 divided by 1 plus 8 e to negative 2x, right? All right, now f of 0 means if I put a 0 here for x, so that would be 1 because e to 0 is 1. 1 times 8 is 8. 8 plus 1 is 9. 150 over 9. What's 150 over 9? 16.7. So that represents the initial amount, right, was present when t was 0, or x was 0 in this case, right, when time is 0. So the variable doesn't matter, x, t doesn't matter. So when x or t was 0, then the initial amount we started with was 16.7. So about right here was 16.7. Then of course it started increasing, right? And reached what? Eventually will reach 150. So 8, find and interpret f of 4. Right? So f of 4 means if you substitute 4 for x, so f of 4 is 150, 1 plus 8 times e to negative 8, right? Now, we can really use calculator and quickly find all of these values. So you go to y equals 2, and we can put 150 divided by, put parentheses for denominator, 1 plus 8, and we need e to the power of negative 2x, and then close the parentheses twice, right? See, I opened it here once, twice, and then 1, 2. Okay, now I'm going to go to table set right here. Second, table set. And I'm going to change this to ask. If it's an auto, you need to move to ask and then press enter. Then I'm going to go to table and then clear whatever is in it. So for example, what is f of x when x is 0? 16.67. That's the number we found, right? Now what is it when x is 4? Well, it's 149.6, which is this number right here. So that's f of 4. That's the amount after 4 interval of times. Now, we are not told here what x is, what the unit of x is, right? If the unit of x is minutes, then this would be after that many minutes. After 4 minutes, there are this many. If the x is in weeks, then that would be after 4 weeks. If it's in years, that would be after 4 years. We have that many. Okay? And then it says find the carrying capacity. Now the carrying capacity would be when x is what? When x is infinity. So basically we want to say what happens. We want to see what happens if x goes to infinity. Well, if it goes to infinity, this right here would be 1 over e to 2 infinity, which is 0, because this number is like really big, and 1 over a really huge number is 0. So that's 0, so we just get 150 over 1. So 150 is the carrying capacity for the population here, whatever it is. And it says graph the model. Now, we have the equation in y1, right? We want to graph it. Well, when we graph it, we change the window. We want the maximum y to be at least 150 because we want to see the carrying capacity. So let's make it less 160, right? And the minimum, of course, we start from 0. We can start from like negative 10 so we can see the graph. And then for x, we don't really want to start from negative numbers because we want to start from 0. And then notice that we found f4 here. And so f4 was what? 149, so it's almost like the capacity at 4, right? So we're going to make it maybe 10, maybe 7 or something, some number. So let's make it 7. There. And then graph. So as you see, it starts from here and then goes up at about this point, flattens, and you see that is the horizontal asymptote. So C here is the horizontal asymptote for this graph. Okay. All right, so that was that. So what I'm going to do, maybe do another what else we can do. So here in 11 and 12, what we want to do, in 11 says determine whether the data from the table could best be represented as a function of as a function that is linear, exponential, or logarithmic. So let's do that. Now we talked about this already. We said that if you take these numbers and if it's linear, then the differences would be the same. If it's exponential, then if you divide, you get the same number. And that would be what it is multiplied by to get the next number. So let's do that. So I'm going to take 0.833 and divide it by 0.694. I get 1.2 something. Then I take now 1 and divide it by previous one. 1 divided by 1 divided by 0.833. And that's almost the same number, right? Approximately 1.2. And then 1.2 divided by 1 is 1.2. So it looks like this is exponential and and the base is 1.2, right? So you can write it like f of x equals to 1.2 to the x power, right? So it's exponential. And you start with 6.694. That means the initial amount must have been just 1, right? So initial amount must have been, 6 point, what am I doing? So so what is multiplied by 1 point is 1.2, right? And then the initial amount must have been what? It's 0.694. So when x equals to 0, we get, no, this is my fault, you don't need that. Because we started with what? We started with x equal to -2 here. So at 0 it should be 1. So initial amount is 1. Okay? And then is that. Of course, before that, if you substitute these numbers, you get what we have here. So we're interested in 0. At 0, that's the initial amount. So it's 1. That's correct. Okay. Now, in number 12, it says rewrite this as an exponential equation. So what we want to do, we want to take this 1.68 times 0.65 to x, and we want to write it as something like, right, we want to write it as something a and then e to some power. We don't know what that power is, right? But we already know, we talked about this. If you have, let's say, b to x, and you want to write it in terms of e, so you want to make sure that you use this idea. ln of, right? If you have ln, if you have e to ln, they cancel each other. And if I put b to x here, e to ln bx is the same as what? Bx. So I can write this b to x as e to ln b to x, which is, if I bring this x downstairs, would be e to x ln b. So that's all I have to do there. So I'm just gonna write this as, I'm going to keep that number 1.68, and this number has to be what? X ln. Now this is ln of the original base, right? So original base was what? The original base is 0.65, right? And now it says write it to 5 significant digits. So we're gonna cut it on up to 5 significant digits. So we're gonna find ln 0.65 with calculator. So what is ln 0.65? So it's negative point, so it's gonna be 1.68 e to negative 0.43078 x, right? So that's 5 significant digits. So now our base is what? E. So we can calculate this with computers and calculators, because if we program everything to work with base E, then it would be very useful to convert everything to that base. So this function is the same as this function with a different base. All right, so now let's do one more here. Well, I'm going to do actually some from the other section. You still have to do this section here. So this section is about also models. This is about fitting exponential models to data. So this is about a logistic growth, okay? So let's do a few of these. So the first problem is, it says what situations are best modeled by logistic equation. I think we talked about this already, but the situations that match the logistic growth are when something growing exponentially at first, but there are some limitations, then it cannot grow exponentially forever. It turns around and it slows down and flattens. Any situation you can think of, for example, number of wild animals in certain region. At first, maybe you have, a few of them, then they start growing. At first, they grow exponentially. Then, of course, there is limitation of food and area, so they start slowing down and then flatten, right? Sometimes federal government actually has to intervene, go to a region and actually reduce the number of wild animals in that region, because according to their calculations, there are going to be a whole lot of them. So they have to do that. All right, so that's logistic, and we talked about that already. Well, let's do some examples. So the first one I want to do here is number 6 to 10 here. So I'm going to get these, and then we are going to keep it on the side, and then look at the graphs that we are given here and see which one matches which one of these, right? So for example, notice that this right here looks like it is increasing exponentially, right? So out of these that we are given, which one is increasing exponentially with positive what? With positive rate of growth. It looks like it's this one right here, right? Is that one here, because that's exponential. You see, that's positive, and looks like this is exponential growth. Now, what about the second one here? Well, second one looks like it is logarithmic. Now, logarithmic at first is the larger rate, then it slows down, That's not logistic. Logistic is exponential first, right? So in logistic, we get exponential first, and then it turns into logarithmic. Here, just logarithmic. Logarithmic looks like, you know, logarithmic graph. Logarithmic graph looks like what? Looks like at first is increasing, then it slows down, right? So that looks like logarithmic. Now, the y-intercept for this is around maybe 2 or something right here, 2, 3. So let's say which one of these is logarithmic. Well, this one is logarithmic, but the minus here makes it flip over what? Flip over x-axis. So if it looks like this and you flip it over, it looks like that, right? So this really doesn't look like the regular log is flipped over, right? So that's not the graph of this. That's not the equation for this. Now, what about this one? Well, this one looks like is logarithmic, and this is plus, so it's looking like this. And the y-intercept for it is around when x is 1, ln 1 would be 0, right? When x is 1, ln 1 is 0, so that's 0, so it's 4.6 something. And at 1, you see is about 4.6 something. So this is actually that graph right there. Okay, now what about this one? Well, this one looks like is decreasing exponentially, or it could also be, so it could be this one, or it could also be what? This one. But what's the y-intercept of this? The y-intercept of this is when x is 0, this would be 1, so it's 10.2 something. So it looks like y-intercept is around 10 point something. So it could be that. I'll go back here. So let's see, we took care of those two. So this one, as I said, the first one is exponential decay because this is negative. And it could also be this one, but the y-intercept of this one, when ln is, let's see, it could be this one right here. So y-intercept of this, when we know when ln is 1, this would be 0, right? If this is 0, that's 5.59. So at 1, it's 5.59, which is close to about right there. So that looks like this graph right here. All right. So the first one, we still have to look for one for it. What about this one? Well, this one looks like is again it looks like it's a growth, but it's a logarithmic growth and a slowing down, right? So could be this one right here, right? It can't be this because the y, when x is 1 here, this has to be 4, so it's not that one. So it could be this one. If that's this one, then that one has to be the other exponential decay. So is it this one? No, it's not that one. So we already took care of that first one right here. So that was exponential. Took care of that one. Took care of this one. And yes, we took care of this one. And we just need the logistic one. So this looks like it's logistic because you see at first it's kind of going up and then it's slowing down. So I would say that this one is the logistic one, which is the last one. So we took care of that too. All right, so again, practice. This is just a practice of seeing these different models have equations that we discussed in this chapter. So what else do we do? Let's do one more thing and then we are done. To the nearest whole number, what is the initial value of a population model or the logistic equation that? What is the carrying capacity? Well, again, you know the initial would be when t equals to 0. So if we put t equal to 0, we can easily find using calculator. So here we have 175 divided by, in this case is 1 plus 6.995, and then e to the power of negative 0.68 x or t, and then close the parentheses twice. Okay, and then we do the same thing. We already have the table set, right? So we go to table, clear those, and put 0. We get 21.88, so that's the answer to the first part, right here. What is the carrying capacity? That's the carrying capacity right there. What's the initial? That's the initial one. So the initial value, right? What is the initial value is 21.88. Now the carrying capacity is basically when x goes to infinity, right? When t goes to infinity. When t goes to infinity, this part right here goes to 0. Why? Because e to negative infinity is really 1 over e to infinity, which is 0. And if this is 0, this is 0, so this is 175 over 1. So 175 is the carrying capacity for this equation. All right, so that was the last thing I wanted to talk about in chapter 6. I'm going to come back here and end this video. I'm going to end this video. I'm going to see you in the next chapter, video on the next chapter. I hope you're doing well. Take care of yourself and others, and I'll see you in the next video.